For the first part of homework 5, we are starting with our process, which we will just combine all of our GC, our GP, and our GM into one term we'll call G, which will be our entire process. And going into this, we have our set point, which in this case will be a sinusoidal input, which we can represent as A sine omega t. And taking the inverse Laplace transform of this and multiplying it by our process, we get G times A omega over s squared plus omega squared, which we can show is equal to the sum of our A over S plus B plus the complex conjugates of our other variables, which in this case we will represent it as an E and an F, which are just numbers, E, F, J over S, W, J plus the complex conjugate of this, which is E minus Fj over S minus Wj. And if we combine these terms, we need to first do the bottom. So we get S squared plus SWJ minus SWJ, and then omega j times omega j is just -1 for our j squared, and then omega squared, so minus omega squared. And these will cancel out, giving us s squared minus omega squared on the bottom. And then our top we'll have to do as well. So we get ES minus EWJ and then we get plus SFJ minus, which will end up being a plus, so we get minus minus plus FW. Then the other side we get ES again. This time we get plus EWJ, and then we get minus SFJ, and this time we get FW, J squared minus plus FW. So what we end up with is these terms cancel out. We have 2 of these and 2 of these. So this simplifies to 2ES plus 2FW all over S squared minus W squared. So we can put this back in. We'll rewrite our equation. So G times A omega t, not omega t, A omega over S squared plus omega squared is equal to sum of A over S plus B plus 2ES plus 2FW over S squared minus W squared. Because on the bottom we had Wj multiplied by negative Wj, we'd end up with W squared, negative W squared times J squared. So that would also give us another negative, meaning this would end up actually being a positive. So plus, plus, plus. Now we can move on. We know that our E is just a number, and so is our F and our omega. So we can represent our 2ES as C, and our 2FW is equal to D, giving us CS plus D over S squared plus omega squared. We know that the inverse Laplace transform of cosine is s over s squared plus w. So if we were to break these apart, we get our cs over s squared plus w squared plus d over s squared plus omega squared. Taking the inverse Laplace transforms of these, we get our coefficient. So c times the cosine of omega t plus w over s squared plus w squared is the inverse Laplace of the sine. However, since there's no w up here, we'll have to include it in our coefficient. So d over w times the sine of omega t. Knowing this, we can go back to our original equation up here, substituting in our cs plus d. So g aw over s squared plus w squared is equal to the sum a over s plus b plus cs plus d over omega, or not omega, s squared plus omega squared. If we multiply across by s squared plus omega squared, we get g aw is equal to the sum of a times s squared plus omega squared over s plus b plus cs plus d. If we were to now let our s be equal to omega j, we know that s squared will be equal to j squared times omega squared, j squared being -1. And if we were to substitute this back in to our equation, we will get our g of jw is equal to aw, not equal to, this stays over here, gaw times aw is equal to the sum of our a s squared, which we know is just equal to -w squared plus omega squared over s plus b plus c omega w plus d. And because w plus -w squared is equal to 0, this whole term is canceled out. From here, we can rewrite our equation again, dividing across by aw, giving us our g of j omega is equal to our c j omega, so c j over a plus d over a omega. And what we can do now is, since our c and a are numbers, we can turn this into another variable, which we will call our I for our imaginary part with our omega. So I is equal to c over a, and our real part, daw, which are all numbers, and our r will be equal to d over aw. So what we can see here is that our c would be equal to ia, and our d, or our d over w is equal to r times a, which we can then substitute back into our equation up here, giving us I times a cosine omega t plus r a times sine omega t, we can represent our I and our R as cosine and sine functions with the phase lag. So our I will be equal to sine theta, and our R will be equal to cosine theta, and now times m. So what we can do is now substitute in our I and our R's and pull out our A and our M. So our A times our M, then we will have sine theta times cosine omega t plus sine omega t multiplied by cosine theta, which we know this expansion of sine and cosines can be simplified to A times M times our sine of omega t plus theta. And what this shows is, as we go back to our original analysis, where do we want to look, is that this is a representation of our system's frequency response. So what we know is that if this comes back higher than 1, so if this is greater than 1, our response to that frequency will continue to increase infinitely, and our system will then blow up. So what we also need to take into account is that this is only when our theta, or our phase lag, is equal to 180 degrees, making our sine function 1. And I think that should be about it. So this shows that when our phase lag is at 180, we need our m to be at a value of 1 or below, or else our system will not be stable.